All right. Hey there. It's Monday, April 6th on Kitchen Table Chemistry here. I hope you had a good weekend. And today we're going to take a look at another gas law as we start or continue our march through the gas laws. Last week we took a look at Charles' Law and Boyle's Law, and this week we're going to take a look at initially what is called Gay-Lussac's Law and then the combined gas law. And this will be all we have time for this week, as it is a short week. We are going to be off Thursday and Friday for the spring break. Okay, initially we looked at this relationship between pressure and volume, and I'm getting my stylus thing out here. Okay, so pressure and volume, if you go back in time, pressure and volume was an inverse relationship like that. The greater the pressure, the less the volume. Then we took a look at volume and temperature, and that's what we did on Friday. So if we had volume and temperature, that was a direct relationship like thus. Today, we're going to take a look at the relationship between pressure and temperature. And pressure and temperature are also going to have a direct relationship if we put pressure here and temperature here, where they are going to both get larger here in the same direction. This is called Gay-Lussac's law. Now, Gay-Lussac's law is written as P1 T2 is equal to P2 T1. And I would take a moment and write that down on my periodic table on the back. I think it would be helpful to have. The temperature is always going to have to be the Kelvin temperature. So it must be Kelvin. And if you think of it, you can also think of it as P1 over T1 is equal to P2 over T2 like that. But I'm thinking that you're probably going to solve it the way that I set it up there on the slide. So Gay-Lussac's law. In Gay-Lussac's law, what must be held constant? Two things. The first is the volume. The volume of the container can't change. If we change the volume, it's going to give us more area for collisions, and that's going to change our pressure. So we can't have that. We're going to keep the volume constant, and the amount of gas in moles has to stay constant. We can't add more gas or take gas away. Again, that's going to change the amount of collisions that we have in here. Hold up a second. No, I'm perfect. This is great. Okay, real life examples of Gay-Lussac's law. A pressure cooker. You may not know what that one there is in the pink, but a pressure cooker is a device that clamps together, the lid clamps down, and it allows you to what is called superheat steam past 100 degrees. And because the volume can't change, you put it on the stove, and the stove heats it up. There's some green flames underneath, and the stove heats it up. And because the temperature goes up, the pressure goes up inside, and that pressure cooks meat a whole lot faster. A car tire is another classic Gay-Lussac's law. We all know that, well, we don't, maybe it's a good idea to know, the tires heat up when you drive. And because they heat up when you drive, the pressure will go up in them as well. So after you've been driving for a while, your tire pressure is likely much greater than it was when you started. Aerosol cans, you might have experienced this because the pressure goes down, the temperature goes down, the cans get cold as you're dispensing them. They're kind of interesting like that. And then lastly, most heaters and your refrigerator will work on some principle of Gay-Lussac's law where they're using temperature and pressure to do this. Yes, the Instant Pot. This thing was a huge craze maybe about 2 years ago. Everybody was getting one. And they cook things on the countertop, and they cook very, very quickly, hence the name Instant Pot. Yes, well, not really an instant, but darn close. They are able to produce a huge amount of heat through pressurization on the countertop, and we'll take a look at this as an example in one of our examples here. So the Instant Pot, typical situation, its volume can't change, but as you heat it up, the pressure inside will change, and that pressure will allow it to cook the food a whole lot faster. Okay, not that one that I wanted. Okay, here we are. Okay, the Instant Pot cooks by using pressure and temperature. What is the temperature of water vapor in an Instant Pot? If it's able to produce 11.6 pounds of pressure, and that's PSI, pounds of pressure, assume 14.7 PSI and 25 degrees Celsius to begin. Well, let's solve this then. What we have here is P1, which is going to be the atmospheric pressure of 14.7 PSI. T1, our initial temperature, is 25 degrees Celsius, which is going to be 298 Kelvin. We must work in Kelvin, always with gas laws, have to be in Kelvin, has to have that absolute scale. P2. Now, P2 is going to be a combination of things here. The situation in the Instant Pot started at 14.7 PSI, and then we added to it 11.6 PSI. And so that's going to give us a total pressure in this Instant Pot of, I have it down, of 26.3 PSI. And then T2 is the X that we're trying to find. So there's our information there. So we put this into Gay-Lussac's law. P1 T2 is equal to P2 T1, where I've got my initial pressure at 14.7 PSI times T2, which is my final temperature, so that is my X, is equal to P2, which is the pressure when it's operating, 26.3 PSI, times T1, which was, when we turned it on, it was at 298 Kelvin, which was the kitchen, which I put the kitchen down as 25 degrees Celsius. That's a bit warm maybe for the kitchen, but probably it is. If we solve this out, I'm going to have the 26.3 PSI times 298 Kelvin divided by 14.7 PSI. This is going to cross out the units of PSI. And it's going to leave me with this T2 value, which I have as X. So T2 is going to end up equaling, initially here, 533 Kelvin. Now 533 Kelvin, again, we're going to want to put that into Celsius. So if we put that into degrees Celsius, that will be equal to 260 degrees Celsius. I'm not going to put it into Fahrenheit for you. You can put it in Fahrenheit for yourself. I refuse to put it in Fahrenheit for you. Don't work with Fahrenheit here ever. Okay, that is our third gas law. It is Gay-Lussac's law. It should be pretty straightforward here. The next thing we're going to do then is to combine all the gas laws together, and curiously, that will be called the combined gas law. And that should be kind of interesting. I'll be sending that off to you tomorrow, and as well as some practice and things to work on Tuesday and Wednesday. I hope you are well, and that I hope that things are proceeding and you're able to understand what's going on. Most of you guys are doing a really great job with the homework and everything and sending stuff to me. This here I have down as 20 points, and I think that's what I'm going to do the marking period is any of these things that you have to send me just because of the aggravation of getting it to me, and that I'm going to put 20 points value on it. When we do tests and things, they will kind of remain around 100 points. So it'll give you a chance to, I'm hoping to hold your grade or where it is, at least hold it where it is. All right. Don't forget the extra credit opportunity that is out there. And again, I hope you are doing well. If you have to go out and still work and you have that job, again, I'm going to say I hope that you're doing okay and that the general public is treating you well and not giving you a hard time. Take care. I will see you tomorrow where we will look at the combined gas law. Adios. Sayonara.